This talk will be about our efforts to reduce the memory requirements of AOSP. This is a project we have spent essentially all of our time on since the last Connect. So our goal was reducing AOSP's memory requirements without hurting performance too badly. We still want to build the devices that are usable, even if they only have 512 megabytes of RAM or so. So what did we try? Picking low-hanging fruits is always the first thing to do, so updating toolchains and just getting benefits automatically was one of the first things. Then making use of new features and updated toolchains. Then we had some ideas for actual code modifications, like splitting libraries into smaller parts, but more on that a bit later. We tried to tweak settings and to replace the memory allocator in the bionic libc, so the Malach family of functions. So first thing we did was update toolchains, see what we can get for free. In Android M, GCC49 is used to compile almost everything. Some parts of the OS are actually built with Clang, mostly Clang 3.6 at the moment. This is going to change in Android N, which will be built completely in Clang 3.8, with GCC essentially going away. But for the lifetime of M, we are replacing GCC49 with the Linaro version of 5.3, and we updated binutils to 2.26 to go along with it. This binutils change doesn't really affect performance, it's just an update that goes well with the newer versions of GCC. Then one of the obvious things to do once you have a new toolchain or something in is make use of its features. There's some things that aren't done by default in AOSP that can help both improve performance and reduce memory usage. For example, if we tell it exactly what CPU we are targeting, like -M CPU equals Cortex A57, and telling it which FPU we have, -M FPU equals Neon FP16, the compiler can generate code that is faster by just making use of what it knows about the CPU, and also smaller, because obviously it can use CPU instructions that aren't guaranteed to be available on other CPUs. And using one CPU instruction will always generate smaller code than having some code that emulates the instruction. There's one drawback with Neon. In order to really make the compiler make use of the Neon instructions, you have to specify -F fast math or its subset -F unsafe math optimizations, because Neon is not as accurate as some of the IEEE standards require. But as far as AOSP is concerned, we haven't seen any ill effects from using -F fast math. So when targeting a low-end device, that might be an advisable flag to use. But if you want to be on the safe side, don't use it. Yeah, some helpful features in toolchains exist even in 4.9 and also in older binutils, but aren't currently being used by stock AOSP. One thing we found to be really effective in reducing memory requirements was just using the -B symbolic linker option. Essentially, that tells the shared linker to bind references to global symbols to the definition in this library without having to go search other linked libraries for other definitions and without having to go through LD preload. This makes the code in the shared library loader a lot less complex and increases application startup time and also reduces memory usage because it doesn't have to keep as many symbol tables and everything in memory at the same time. On a pretty similar thing, -F visibility equals hidden and -F visibility equals protected. There are two compiler flags that can hide symbols to the world outside of the specific compilation unit, so the binary or library currently being built. And making use of those allows the compiler to throw away some code when it sees that code is not actually being used. And it also reduces the binary size because the symbol table gets smaller. And the symbol table is mapped into memory, so that also helps with RAM usage. So one of the modifications in actual code we've looked into was splitting libraries into smaller parts. Many libraries come with a lot of functionality, but some of that isn't used all that extensively. For example, we have libpng, libjpeg, libgif, and everything, all the image codecs, where the decoder is used by pretty much everything. The launcher uses libpng for drawing icons and libjpeg for looking at the desktop background and everything, but none of those things actually use the encoding part. So getting rid of the encoder and just making that loadable on demand should save a bit of memory. The same could be done for zlib, where decompression is used frequently, including in libpng, and compression is only used once in a while. Next thing was tweaking settings. For example, art has a lot of settings that affect its memory use. Heap start size equals whatever tells it how much heap to allocate on startup. Heap growth limit tells it how big the heap can grow. Heap size is the standard size. Target utilization allows adjusting how much memory it keeps reserved for the process without trying to use GC to throw away stuff. Min-free tells it at what point it needs to start grabbing more memory when it has used up everything but heap min-free. And max-free is a setting that tells it can free up memory to other processes when they are not being used. The default settings are all much higher than what we are listing here. What we are listing here has been shown to work pretty well for low memory devices. So that's another way to make more memory available, just to tweak the art settings to make sure it frees up stuff early and doesn't over-allocate. Of course, this comes with a slight drawback in performance. So the next thing was replacing the memory allocator. Bionic already comes with two versions of Malach, JE-Malach and DL-Malach. JE-Malach is what's used in Bionic by default. The reason why they are doing that is that it scales really well with many CPU cores. DL-Malach, on the other hand, is much more efficient with low memory devices. Just switching the allocator saved us around 20 megabytes of RAM after boot up. But the drawback is it doesn't scale that well with many CPU cores, so on a higher end 64-bit devices you'll see performance drops. And it looks like Upstream has plans to actually remove the DL-Malach implementation from Android N because they care more about the scalability than usability on low memory devices. So we've looked into this some more and asked the question if there's any Malach implementation that would bring us both the advantages of JE-Malach and DL-Malach. So we are looking for a Malach implementation that will both scale well and work well on low-end devices. We've already investigated JE-Malach and DL-Malach, the ones that are already included in the Bionic. We've also looked at PT-Malach 2 and PT-Malach 3. That's a different implementation that is pretty close to what's being used in glibc, but we found it wastes more memory than dlmalloc, not quite as much as jemalloc, but it didn't turn out to be a significant improvement. We are still looking at other malloc implementations. TLSF malloc is a version of malloc that was written specifically for embedded devices, so that might help us save even more memory than with dlmalloc. But this investigation is still going on. We have a patch that makes everything compile, but TLSF malloc lacks some functions that are implemented by the other malloc implementations. And apparently those functions are relevant in AOSP because we see a lot of crashes at runtime at the moment. So this has to be fixed, and this investigation is still in progress. And there's tcmalloc, netmalloc. We haven't started looking into those yet. We will start looking after we are done with TLSF malloc. And then another thing we found interesting is the malloc implementation in the muscle C library that uses essentially the same algorithm as dlmalloc, but it has much more fine-grained locking, so it might solve at least some of the scalability issues. This investigation also isn't finished. The final results will be updated when we have all that. Overall results, we managed to save about 200 megabytes in the use case of second boot and opening the browser, pointing it at linaro.org. While performance, which is shown in the green line, has remained more or less constant. So the green line is the AnTuTu benchmark scores, red line is memory usage after starting the browser, blue line is used memory just after boot up without doing anything, and the yellow line is Quadrant Pro benchmark scores. So as you can see, memory use always went down, and benchmark results remained pretty much the same and actually increased slightly. One interesting thing is that the low-hanging fruit were actually more effective than some of the more advanced things we tried to do. So with toolchain features and switching malloc implementations, adjusting a couple of art settings, we could achieve much more than with splitting libraries into different parts, even though that was much more work. So sometimes small changes can actually be much more effective than bigger changes. There's some more room for optimizations. So one thing that hasn't been done at all in terms of the diagram we've shown was looking at kernel settings. And there is stuff like setramfs, which essentially takes a pile of memories and uses that as a swap partition, but compresses it. So you can more or less double the amount of memory, but it comes with a performance drawback because compression obviously costs CPU cycles. But for a low memory device, this is probably very useful. The reason why we haven't been able to look at that in detail is that we haven't had a test device that can handle a current kernel, and setramfs doesn't exist on the old kernels that were used for the Nexus 7. But the good news is this has been fixed. We have a Nexus 7 booting to UI on current kernels now. You can look at that in Friday's demo sessions. So now we can also investigate this area of memory optimizations and update numbers a little more. So another kernel feature that comes in there that we can start testing now that we have the updated Nexus 7 kernel is KSM, kernel same page merging. That's essentially a feature in the kernel that scans the different memory pages and sees when several pages are the same, and then it just replaces them with references to the same. The kernel also comes with different memory allocators, SLOB, SLUB, SLAB. Probably the SLOB allocator should be used for low RAM kernels, but that is another place where we trade memory efficiency for performance. So what else could be done that we haven't done so far? Investigating more Malach implementations is in progress. Then we've had the idea of re-implementing some Java-based components in C and C++ because that would eliminate some of the overhead of the various runtime libraries. But that's another thing that's going to be a lot of work with probably not all that much benefit, because with all the apps in the background, Java stuff is going to be running anyway. Another thing that is currently being worked on is checking memory efficiency of various file systems. And then pretty much all the investigations we've done so far have been done in a 32-bit world, because that was the target set by members. And now we are repeating some of the investigations in the 64-bit world, checking which changes are still efficient there, what things should be reverted for 64-bit devices. And we've also found a couple of places where we can make some 64-bit specific optimizations. For example, we found a couple of pieces of code that have assembly implementations for ARMv7 but not ARMv8, and the assembly implementations were much shorter than the C implementations that were used as a fallback. Yeah, that's pretty much the overview of the project. So for the rest of the time, we can take questions and talk about other optimization opportunities. Could someone pass around mics?
The Windows Phone use swap into file system, Flash. Have you tried that?
That is something the kernel can do, obviously, but we think it's not a very good idea because it's not very performant, and also because it wears down.
You don't have any excuse not to do it. If Microsoft can do it, the people in this room can do much better.
Maybe we should also display a blue screen here.
That's a joke.
So I think it's...
You can't tell me that you don't think it will work without having tried it.
It will work, obviously, but it will wear down the flash because those things are...
Windows Phone use the same damn flash.
So is your question about using hibernation on ARM devices? No.
Just swap into file.
Oh, swap into file.
Yeah, so it can definitely be done, but...
I mean, you're not the first one told me that. So it's probably true, but I just want to know people who have done testing and give me data, not just telling me it can be done. Because the Windows guys tell me it's done, works, no problem. Maybe they lied to me, but I don't see.
But
Well, no, they didn't lie. You can do it. You can just enable it. Essentially, you can either have a partition to swap to, or you can just create a file inside the file system and swap to that.
No, I know how to do it. I just want
Yes.
to know the testing is the hard part.
Yeah, it does work. We have run a couple of experiments there, but we think it's not the best of ideas because it wears down the flash and because of performance issues. But
The way the
yeah.
argument doesn't work.
Yes.
Tell me how much shorter you think it is. 4 months, you'll die?
You'll die.
Okay, cool. That's the answer.
Yeah.
Okay, so a question, can you go back to the page on the Malach? So a question.
This one?
Oh, there are several candidates of the Malach you investigated. Also, my
Yeah,
question is, are you looking for the most space efficient or memory efficient Malach implementation for?
Yes,
for
exactly.
the work? So do you worry about the scalability and the speed? I mean the time efficiency at the same time?
Yes. That's why we are looking at so many other options. We found that so far DL Malloc is most efficient in just preserving memory, and JE Malloc is better in performance, especially with multiple cores. But we are not really happy with either implementation. That's why we are still investigating all the other options. And we'll have an update later when all the other ones are investigated, and then we'll have some advice on whether or not any of them can beat both DL Malloc and JE Malloc.
So, my question is, any plans to evaluate LZ4 and SquashFS because these features are available on 4.0 plus kernel?
Yes, that's another thing we're going to look at. I've already mentioned we are looking at different file systems. What was that? Yeah. So that's another thing we are going to look at some point. Right now we are using the X4 file system because that's the standard, but we think that's probably, especially when you're also short on disk space, there's probably a point to be made for SquashFS with LZ4.
You mentioned switching Java-based components to C++. Do you have any in mind?
Not really. That was one of the things we just had on the list early on of the things that might be doable to reduce memory usage. And then we decided it would be too much effort to reach the target by the given timeline. But essentially, anything that is near the lower end of the stack would be an interesting target. So one thing that I've been thinking might be interesting is the window manager stuff. Maybe even some parts of the launcher, just stuff that will always be in memory. But that's actually a good question. So does anyone have better ideas of what we could be targeting there if we were to run a follow-up project? Okay, doesn't look like it. Do we have other questions?
So a lot of devices use carve-outs. Have you looked at actually ways to actually replace the need for carve-outs to actually not waste a lot of memory, because the carve-outs usually allocate memory for the worst case scenario. So actually to avoid having carve-outs in the system.
We haven't looked at that yet, but that's a good point.
So have you measured what was performance drop? So your plot shows that memory reduced, but have you measured for each step what was actually a performance drop, or maybe it even?
Yes.
Yeah.
And the interesting thing is performance remained pretty much the same. If you look at this, the green line is benchmark results from Antutu, and the orange line is benchmark results from Quadrant Pro. So some optimizations made it go up a little, some made it go down a little, but overall performance remained pretty much constant. So one thing that actually reduces performance a little is switching compiler flags to include -OS for GCC or -OZ for Clang, which means optimize for size more than for performance. But the other optimizations, like just updating the compiler and making use of -M CPU equals and -M FPU equals for targeting exactly right CPU and so more than made up for it. And also stuff like -B symbolic linker flags and so on tend to help performance as well. And with the Malach implementations, it is really hardware dependent. On a device that only has 1 or 2 CPU cores, you don't see any performance drop with the Malach. But when you start running it on a box with 8 cores, you see quite a bit of a performance drop. Okay, does that answer it? Do we have anything else?
You mentioned the toolchain, Malach, and settings were more effective than the library splitting. Do you have a split up as to which gave you the best bang for the buck?
Yes, essentially, you can see it here. The indicators on the bottom show what we have done to achieve a particular move in the lines. So the first big drop was just switching to GCC 5.3. Then we have a small drop from CPU-specific flags, another small drop from target optimized for size, which is a flag we introduced to just add a couple of settings and switch the compiler flags to -OS for GCC and -OZ for Clang. Then we have another bigger drop for minor tweaks, which was all sorts of smaller things like splitting up libraries. Then we have another drop from reducing logging, which wasn't mentioned separately, but that was essentially just reducing the log level that is enabled by default in user builds. And we have another relatively big drop from using -B symbolic. Not a lot of change from the strict aliasing patch set. Not a lot of change from visibility equals hidden, which might come as a bit of a surprise, but if you use visibility equals hidden without using -B symbolic, it actually shows a lot of performance, but those two flags are somewhat mutually exclusive because both try to optimize the same thing. Both will just help shrink the symbol table. So if you do one, the other becomes kind of obsolete. And then that last bigger drop we see in the red line was just caused by config options, which was mostly setting the art settings to this.
Thank you. I think GCC was the biggest differentiator, at least in terms of percentage.
Yes. If you just look at the red line, GCC made a big difference. So the red line is used RAM after starting the browser and pointing it at linaro.org. And if you look at the blue line in comparison, that shows memory usage just after booting the system without doing anything. And you'll see that it behaves slightly differently. The red line goes down quite a bit from just a switch to GCC, while the blue line shows almost no change at that point. And that is because Chromium is essentially written in C and C++, while the rest of the system relies more on Java bits. So it is not safe to assume that just switching the compiler will automatically drop your memory use to 80% or so, but that is rather use case specific.
Question. So as far as I can tell, using the N22 as the performance index for this case probably is not a good idea, because most of N22 tests are not memory sensitive. Actually, most of them use just a little bit of memory, and a lot of them are, well, just stay in L1 or L2 cache, doesn't really use DRAM. And so, as you can see, the performance is not affected by the memory reduction.
Yes, that's true. Essentially, we ran all those regular benchmarks to just make sure that the extra stuff being done doesn't generally slow the system down. We've seen some tests where actually performance went down a lot, which happened, for example, when we tried to compress everything in memory, experimenting with ZRAMFS and almost no uncompressed memory. And so those were things that we immediately backed out. And obviously, if you have a benchmark that is actually a lot more memory intensive, you might see somewhat different results. Especially with the Malach change, you might see somewhat different results there. So we have used benchmarks that exist. We didn't write any new benchmarks. If you have any particular benchmarks that you'd like us to run, we are more than open to the idea. Okay, does that answer it? Okay, there's another question there.
Hi. Actually, I have two questions. One is related to the benchmarking. So, whether this thing has been up and running on any like a smartphone, like reduced memory, like for example, Android L running under like 512, how that works. So, so that's one question. Not just the benchmarking, but on real phone, and people try this, whether can really running well under like 512. That's first question. The second question is most of this technology is applied to the kernel level or toolchain, whether it's considered to also do something in the framework level. For example, you mentioned rewrite the thing, but also there's something like a scheduler, like the task management, like even the display buffer management, whether there's some consideration to also do something in that level. Thanks. Two questions.
Okay, so to answer the first question, we did essentially all our testing on Nexus 7, which has quite a bit of memory, but which probably could count as a low memory device these days. And we have done some testing on Thundersharks that only have 512 megabytes. But of course, those are development boards, and we don't have any real-world phones to do use cases testing with. So that is actually a bit of a problem. We just don't have access to enough test hardware. And it would be good if members could just supply us with more test hardware that comes closer to use cases they want us to seed. And for the second part of the question, we didn't look into the schedulers and similar things in too much detail yet. Does that answer it?
During your study, is fragmentation ever a problem?
You mean memory fragmentation? Yeah, that becomes a problem with some of the Malach implementations, but overall it hasn't been a big problem.
How do you define it's not a problem?
We define it by seeing that a lot of memory just is marked as used when it actually isn't, so over allocating stuff because there's chunks that should really be merged into one. And also when it just comes down to performance, so when we see the real drop in benchmark numbers.
Have you seen any benchmark reduced or gets worse because of the fragmentation when the memory pressure is high?
Yeah, we've seen a couple of things only when the memory pressure was really getting high, but it always recovered when the memory pressure was taken out again by, for example, closing an app or so.
Right. Do you have data that I can take a look?
No real hard data, because that was mostly a matter of using ADB and dumps as mem info while...
The performance data, when you say when the memory pressure is high, you see some degradation in some benchmarks?
Yeah, it was mostly manual testing, so...
Like what kind of benchmark?
Using benchmarks on all sorts of different apps while the patches were running and just trying to use the device as if it were a real-world situation.
Real-world situation, so app launch time, browser load time, that kind of thing?
Yes. So launch a browser, play a game and stuff like that. So essentially
Is
manual.
it noticeable performance degradation when the fragmentation could be high under memory pressure, or is it not because of fragmentation, it's just because the allocator takes longer to get memory?
Yeah, for the most part it's just because more stuff starts happening in the background because, for example, the garbage collector starts being more active and yeah, so obviously also the allocators become somewhat slower, but we don't have any real hard numbers on that. That is more a result of trying to use the device and just getting a feel for it.
Yeah, I asked because I work for a company where we do hardware. I just want to make sure the hardware is handling QB pressure under fragmentation situations. It sounds like actually can't tell. Yeah, so you're also as expected.
Okay, do we have anything else?
I remember that one of earlier tasks or topics to work on was trying different libc implementations with Android, in particular Muscle. So any progress on that?
Not really, because that has essentially finished about 8 months ago. We weren't trying to change the entire libc because we were trying to preserve binary compatibility, but we've investigated all sorts of functions in one libc and copied them into Bionic and then checked which implementation works better. Most of the time Bionic actually had the better performing implementation already, and for some of the things we ended up copying code from Muscle and upstreaming it into Bionic.
Okay, thank you.
Okay, anything else? Doesn't look like it, so thank you for attending.